This is example number 1 for vector calculus. You may want to pause the video and take notes of the example description. So the problem says that the coordinates of a particle are given as a function of time by the following equations. You have r equal to 8 time squared. Theta, this is t, by the way, time. And then theta is equal to b times t, z is equal to c times t q plus d. R, theta, and z are expressed in the cylindrical coordinate, and a, b, c, d are constant. We want to find in the problem all the components that we are looking for. Okay, so the first thing we want to find is the position vector. So let's see how we write the position vector in cylindrical coordinates. Position vector of a particle. Okay, the cylindrical vector of a particle will be r er plus z ez. Okay, that's just by definition, that's how it is. Theta doesn't come into the picture because the position vector does the following. You have this, you want to come to a location here, right? And that vector basically is decomposed in what's happening in the r direction and how much it moves in the z direction. Okay, so there is a component here only in the r and only in the z, and that's how you find your position vector. So in the problem, you found that r and theta given by the following values. So if I replace them here, this is at squared er plus ctq plus d times ez, the unit vector ez. Okay, so the second question you want to ask for is the velocity vector. The velocity vector now is given by the following. You want to take the time derivative of r with respect to time, with respect to t, and that would be r dr dt, okay, plus dr dt dr plus dz dt ez plus z dz respect to t. You're taking the time derivative of each of these quantities. You see, r times d theta, r times er, derivative of er respect to time, plus time derivative of this times this, and the first term and the second term, and they're using the chain rule. That's what we did here. Okay, so now we're going to go ahead and you have to know by definition that all the time derivative in z, they're actually equal to 0. Okay, we have all time derivatives in moving in the r direction. Remember, this is your r direction. This is your z direction right here. Okay, this is z direction. So, and this is your theta direction. Okay, so if you remember from our derivation in class, this was actually equal to d theta e theta. We derived this in class. So we're going to use this very handy, and we're going to do some replacements. Okay, because you can see here, this term right here, I have a dr, okay, so I can replace it by this. So by doing that replacement, now you can write your velocity vector as r d theta dt e theta plus dr dt er plus dz dt ez. Remember, the other term was actually equal to 0. It is gone. So you end up with 3 terms. So now you know what your r is, you know what your theta is, right? That's given in the problem, r, theta, and z. So we're going to just replace the values in here, and you see that this is equal to r times b, right? Derivative of this respect to time is b, e theta, plus this respect to time is 2 times a times t, 2 times a respect to t, er, plus dz respect to time, this goes away and does 3 times ct squared. So this is 3 times ct squared ez. And you know what your r is, right? Your r is a times t squared, so we replace it in there. So you end up with the expression, your whole expression looks like this. 2 times at er, bringing this up front, plus a b t squared e theta, plus 3c t squared ez. This is your velocity vector. Okay. Now you may ask, okay, so what is the velocity? I had the velocity, I want the acceleration. Okay, so let's go ahead and find the acceleration for this exercise. So the acceleration will be the derivative of v respect to time. Okay, so it will be derivative of the first term, 2 times at er, plus that term, first term, plus derivative of er respect to time. That is your first term. That is this term right here. Now we will do the second term, plus derivative of time of a b t squared times e theta, plus a b t squared times e theta et. Now we do the second term, that's this term right here, plus derivative of time respect to 3 times t squared ez, plus 3 times ct squared derivative of ez respect to time, and again this is equal to 0, right? And we know that, and we derived this in class, dr is equal to d theta e theta. We know that d theta is equal to minus d theta er. So we have some of these expressions that we can replace. You can see I have this term here, I have dr here, so those terms get replaced by this. So let's go ahead and do some math here. And rest becomes a pure exercise of mathematics, doing math. I'm going to just go ahead and write some of these expressions here. 2 times at, replacing all those variables in there, plus 2abt e theta, plus abt squared minus d theta dt er, plus 6t e theta, right? So now what you realize is that this term right here is taking the derivative right here. This it becomes a constant. So your end result, after you combine all the terms, you got an r here, theta and theta, and you can do all the math. You end up with the following expression. Um, I'm skipping some of the mathematics in here, but if you have any questions, please let me know. Work out the math on your own. This becomes pretty much straightforward. Plus 6 times ct e theta. Okay, easy. So this is the expression of acceleration that you have. It is so this is one way to do the problem, right? And how to find the acceleration given for a particle once we have all those answers, right? And then there will be another example, a homework problem that's very similar that you will be required to actually do it on your own. Okay? This concludes example number 1.